to mate with the passengers we took on board at station 5,990,000 years ago, and probably those from station 5,900,000 years ago too, but probably not those who joined us at station 4 million years ago. Let's now resume our 10,000-year hops all the way back to station 25 million years ago. There we shall find your and my 1.5 million great-grandparents as an approximate estimate. They will not be apes, for they will have tails. We would call them monkeys if we met them today, although they are no more closely related to modern monkeys than they are to us. Although very different from us and incapable of breeding with us or with modern monkeys, they will breed happily with the all but identical passengers who joined us at station 24,990,000 years ago. Gradual change all the way. On we go, back and back, 10,000 years at a time, finding no noticeable change at each stop. Let's pause to see who greets us when we reach station 63 million years ago. Here we can shake hands, or should that be pause, with our 7 million great-grandparents. They look something like lemurs or bush babies, and they are indeed the ancestors of all modern lemurs and bush babies, as well as the ancestors of all modern monkeys and apes, including us. They are as closely related to modern humans as they are to modern monkeys, and no more closely to modern lemurs or bush babies. They wouldn't be able to mate with any modern animals, but they would probably be able to mate with the passengers we picked up at station 62,990,000 years ago. Let's welcome them aboard the time machine and speed on backwards. At station 105 million years ago, we'll meet our 45 million great-grandfather. He's also the grand ancestor of all the modern mammals except marsupials, now found mostly in Australia, plus a few in America, and monotremes, duck-billed platypuses and spiny anteaters, now found only in Australia and New Guinea. He's equally closely related to all modern mammals, although he may look a bit more like some of them than others. Station 310 million years ago presents us with our 170 million great-grandmother. She is the grand ancestor of all modern mammals, all modern reptiles, snakes, lizards, turtles, crocodiles, and all dinosaurs, including birds, because birds arose from within the dinosaurs. She is equally distantly related to all those modern animals, although she looks more like a lizard. What that means is that lizards have changed less since her time than, say, mammals have. Seasoned time travelers as we are by now, it isn't far to go until we hit the fish that I mentioned earlier. Let's make one more stop on the way, at station 340 million years ago, where we meet our 175 million great-grandfather. He looks a bit like a newt, and is the grand ancestor of all modern amphibians, newts and frogs, as well as of all the other land vertebrates. And so to station 417 million years ago, and your 185 million great-grandfather, the fish that we met before. From there we could go on even further back in time, meeting more and more distant great-grandparents, including various kinds of fish with jaws, then fish without jaws, then our knowledge starts to fade into a kind of mist of uncertainty, for these very ancient times are where we start to run out of fossils.
DNA tells us we are all cousins. Although we may lack the fossils to tell us exactly what our very ancient ancestors looked like, we are in no doubt at all that all living creatures are our cousins and cousins of each other. And we also know which modern animals are close cousins of each other, like humans and chimpanzees, or rats and mice, and which are distant cousins of each other, like humans and cuckoos, or mice and alligators. How do we know? By systematically comparing them. Nowadays, the most powerful evidence comes from comparing their DNA. DNA is the genetic information that all living creatures carry in each of their cells. The DNA is spelled out along massively coiled tapes of data called chromosomes. These chromosomes really are very like the kind of data tapes you'd feed into an old-fashioned computer, because the information they carry is digital and is strung along them in order. They consist of long strings of code letters, which you can count. Each letter is either there or it isn't. There are no half measures. That's what makes it digital, and why we say DNA is spelled out. All genes in every animal, plant and bacterium that has ever been looked at are coded messages for how to build the creature, written in a standard alphabet. The alphabet has only 4 letters to choose from, as opposed to the 26 letters of the English alphabet. We write the DNA letters as A, T, C, and G. The same genes occur in many different creatures, with a few revealing differences. For example, there's a gene called FOXP2, which is shared by all mammals and lots more creatures besides. The gene is a string of more than 2,000 letters. You can tell that FOXP2 is the same gene in all mammals because the great majority of the code letters are the same. Not quite all the chimpanzee letters are the same as ours, and somewhat fewer of the mouse ones are. Of the total of 2,076 letters in FOXP2, the chimpanzee has 9 letters different from ours, while the mouse has 139 letters different. And that pattern holds for other genes too. That explains why chimpanzees are very like us, while mice are less so. Chimpanzees are our close cousins. Mice are our more distant cousins. Distant cousins means that the most recent ancestor we share with them lived a long time ago. Monkeys are closer to us than mice, but further from us than chimpanzees. Baboons and rhesus macaques are both monkeys, close cousins of each other, and with almost identical FOXP2 genes. They are exactly as distant from chimps as they are from us, and the number of DNA letters in FOXP2 that separate baboons from chimps is almost exactly the same, 24, as the number of letters that separate baboons from us, 23. It all fits. And just to finish off this little thought, frogs are much more distant cousins of all mammals. All mammals have approximately the same number of letter differences from a frog, for the simple reason that they are all exactly equally close cousins. All mammals share a more recent ancestor with each other, about 180 million years ago, than they do with the frog, about 340 million years ago. But of course not all humans are the same as all other humans, and not all baboons are the same as all other baboons, and not all mice are the same as all other mice. We could compare your genes with mine letter by letter, and the result? We turn out to have even more letters in common than either of us does with a chimpanzee. But we'd still find some letters that are different. Not many, and there's no particular reason to single out the FOXP2 gene. But if you counted up the number of letters all humans share in all our genes, it will be more than any of us shares with a chimpanzee. And you share more letters with your cousin than you share with me. And you share even more letters with your mother and your father, and if you have one, with your sister or brother. In fact, you can work out how closely related any two people are to each other by counting the number of DNA letters they share. It's an interesting count to make, and it is something we are probably going to hear more about in the future. For example, the police will be able to track somebody down if they have the DNA fingerprint of his brother. Some genes are recognizably the same, with minor differences, in all mammals. Counting the number of letter differences in such genes is useful for working out how closely related different mammal species are. Other genes are useful for working out more distant relationships, for example between vertebrates and worms. Other genes, again, are useful for working out relationships within a species, say for working out how closely related you are to me. In case you're interested, if you happen to come from England, our most recent shared ancestor probably lived only a few centuries back. If you happen to be a native Tasmanian or a Native American, we'd have to go back some tens of thousands of years to find a shared ancestor. If you happen to be a Kung San of the Kalahari Desert, we might have to go back even further.
Chapter 3. Why are there so many different kinds of animals? There are lots of myths that attempt to explain why particular kinds of animals are the way that they are. Myths that explain things like why leopards have spots and why rabbits have white tails. But there don't seem to be many myths about the sheer range and variety of different kinds of animals. I can find nothing akin to the Jewish myth of the Tower of Babel, which accounts for the great variety of languages. Once upon a time, according to this myth, all the people in the world spoke the same language. They could therefore work harmoniously together to build a great tower, which they hoped would reach the sky. God noticed this and took a very dim view of everybody being able to understand everybody else. Whatever might they get up to next, if they could talk to each other and work together? So he decided to confound their language, so that they may not understand one another's speech. This, the myth tells us, is why there are so many different languages, and why, when people try to talk to people from another tribe or country, their speech often sounds like meaningless babble. Oddly enough, there is no connection between the word babble and the Tower of Babel. I was hoping to find a similar myth about the great diversity of animals, because there is a resemblance between language evolution and animal evolution, as we shall see. But there doesn't seem to be any myth that specifically tackles the sheer number of different kinds of animals. This is surprising because there is indirect evidence that tribal peoples can be well aware of the fact that there are many different kinds of animals. In the 1920s, a now famous German scientist called Ernst Mayr did a pioneering study of the birds of the New Guinea highlands. He compiled a list of 137 species, then discovered, to his amazement, that the local Papuan tribesmen had separate names for 136 of them.
Back to the myths. The Hopi tribe of North America had a goddess called Spider-Woman. In their creation myth, she teamed up with Tawa, the sun god, and they sang the first magic song as a duet. This song brought the earth and life into being. Spider-Woman then took the threads of Tawa's thoughts and wove them into solid form, creating fish, birds, and all other animals. Other North American tribes, the Pueblo and Navajo peoples, have a myth of life that is a tiny bit like the idea of evolution. Life emerges from the earth like a sprouting plant, growing up through a sequence of stages. The insects climbed from their world, the first or red world, up into the second world, the blue world, where the birds lived. The second world then became too crowded, so the birds and insects flew up into the third or yellow world, where the people and other mammals lived. The yellow world in turn became crowded and food became scarce, so they all, insects, birds and everybody, went up to the fourth world, the black and white world of day and night. Here the gods had already created cleverer people who knew how to farm the fourth world and who taught the newcomers how to do it too. The Jewish creation myth comes closer to doing justice to diversity, but it doesn't really attempt to explain it. Actually, the Jewish holy book has two different creation myths, as we saw in the previous chapter. In the first one, the Jewish God created everything in 6 days. On the fifth day he created fish, whales and all sea creatures, and the birds of the air. On the sixth day he made the rest of the land animals, including man. The language of the myth pays some attention to the number and variety of living creatures. For example, God created great whales and every living creature that moveth, which the waters brought forth abundantly after their kind, and every winged fowl after his kind, and made every beast of the earth, and everything that creepeth upon the earth after his kind. But why was there such variety? We are not told. In the second myth, we get some hint that the god might have thought his first man needed a variety of companions. Adam, the first man, is created alone and placed in the beautiful oasis garden. But then the god realized that it is not good that the man should be alone, and he therefore formed every beast of the field and every fowl of the air, and brought them unto Adam to see what he would call them.
Why are there really so many different kinds of animals? Adam's task of naming all the animals was a tough one, tougher than the ancient Hebrews could possibly have realized. It's been estimated that about 2 million species have so far been given scientific names, and even these are just a small fraction of the number of species yet to be named. How do we even decide whether two animals belong in the same species or in two different species? Where animals reproduce sexually, we can come up with a sort of definition. Animals belong to different species if they don't breed together. There are borderline cases like horses and donkeys, which can breed together but produce offspring, or mules or hinnies, that are infertile, that is, that cannot have offspring themselves. We therefore place a horse and a donkey in different species. More obviously, horses and dogs belong to different species because they don't even try to interbreed and couldn't produce offspring if they did, even infertile ones. But spaniels and poodles belong to the same species because they happily interbreed, and the puppies that they produce are fertile. Every scientific name of an animal or plant consists of two Latin words, usually printed in italics. The first word refers to the genus or group of species, and the second to the individual species within the genus. Homo sapiens, wise man, and Elephas maximus, very big elephant, are examples. Every species is a member of a genus. Homo is a genus, so is Elephas. The lion is Panthera leo, and the genus Panthera also includes Panthera tigris, tiger, Panthera pardus, leopard or panther, and Panthera onca, jaguar. Homo sapiens is the only surviving species of our genus, but fossils have been given names like Homo erectus and Homo habilis. Other human-like fossils are sufficiently different from Homo to be placed in a different genus. For example, Australopithecus africanus and Australopithecus afarensis. Nothing to do with Australia, by the way. Australo just means southern, which is where Australia's name also comes from. Each genus belongs to a family, usually printed in ordinary Roman type with a capital initial. Cats, including lions, leopards, cheetahs, lynxes, and lots of smaller cats, make up the family Felidae. Every family belongs to an order. Cats, dogs, bears, weasels, and hyenas belong to different families within the order Carnivora. Monkeys, apes, including us, and lemurs all belong to different families within the order Primates. And every order belongs to a class. All mammals are in the class Mammalia. Can you see the shape of a tree developing in your mind as you hear this description of the sequence of groupings? It is a family tree, a tree with many branches, each branch having sub-branches, and each sub-branch having sub-sub-branches. The tips of the twigs are species. The other groupings, class, order, family, genus, are the branches and sub-branches. The whole tree is all of life on Earth. Think about why trees have so many twigs. Branches branch. When we have enough branches of branches of branches, the total number of twigs can be very large. That's what happens in evolution. Charles Darwin himself drew a branching tree as the only picture in his most famous book on the origin of species. He sketched an early version in one of his notebooks some years earlier. At the top of the page, he wrote a mysterious little message to himself. I think. What do you think he meant? Maybe he started to write a sentence and one of his children interrupted him, so he never finished it. Maybe he found it easier to represent quickly what he was thinking in this diagram than in words. Perhaps we shall never know. There is other handwriting on the page, but it is hard to decipher. It is tantalizing to read the actual notes of a great scientist written on a particular day and never meant for publication. The following isn't exactly how the tree of animals branched, but it gives you an idea of the principle. Imagine an ancestral species splitting into two species. If each of those then splits into two, that makes 4. If each of them splits into two, that makes 8, and so on through 16, 32, 64, 128, 256, 512. You can see that if you carry on doubling up, it doesn't take long to get up into the millions of species. That probably makes sense to you, but you may be wondering why a species should split. Well, it's for pretty much the same reason as human languages split. So let's pause to think about that for a moment.
Pulling apart how languages and species divide. Although the legend of the Tower of Babel is, of course, not really true, it does raise the interesting question of why there are so many different languages. Just as some species are more similar than others and are placed in the same family, so there are also families of languages. Spanish, Italian, Portuguese, French, and many European languages and dialects, such as Romansh, Galician, Occitan, and Catalan, are all pretty similar to each other. Together, they're called Romance languages. The name actually comes from their common origin in Latin, the language of Rome, not from any association with romance. But let's use an expression of love as our example. Depending on which country you are in, you might declare your feelings in one of the following ways. Ti amo, amote, t'aimi, or je t'aime. In Latin, it would be te amo, exactly like modern Spanish.
To swear your love to someone in Kenya, Tanzania, or Uganda, you could say in Swahili, nakupenda. A bit further south in Mozambique, Zambia, or Malawi, where I was brought up, you might say in the Chinyanja language, ndimakukonda. In other so-called Bantu languages in southern Africa, you might say ndinokuda, ndiakutanda, or to a Zulu, ndiakuthanda. This Bantu family of languages is quite distinct from the Romance family of languages, and both are distinct from the Germanic family, which includes Dutch, German, and the Scandinavian languages. See how we use the word family for languages, just as we do for species, the cat family, the dog family, and also, of course, for our own families, the Jones family, the Robinson family, the Dawkins family.
It isn't hard to work out how families of related languages arise over the centuries. Listen to the way you and your friends speak to each other and compare it to the way your grandparents speak. Their speech is only slightly different, and you can easily understand them, but they are only 2 generations away. Now imagine talking not to your grandparents, but to your 25 great-grandparents. If you happen to be English, that might take you back to the late 14th century, the lifetime of the poet Geoffrey Chaucer, who wrote descriptions like this.
Here was a lord full fat and then God point, his e'en staper and rolling in his head, that stemmed as a fornice of a lad. His boat as souple, his horse in great estate, no certainly he was a fire prelate. He was not pale as is a 4-peen ghost, a fat swan loved he best of ane roast. His palfrey was as brune as is a berry.
Well, it is recognizably English, isn't it? But if it were any more different, you'd probably consider it a separate language, as different as Spanish is from Italian. So the language in any one place changes century by century. We could say it drifts into something different. Now add the fact that people speaking the same language in different places don't often have the opportunity to hear each other, or at least they didn't before telephones and radios were invented, and the fact that language drifts in different directions in different places. This applies to the way it is spoken as well as to the words themselves. Think how different English sounds in a Scottish, Welsh, Geordie, Cornish, Australian or American accent. And Scottish people can easily distinguish an Edinburgh accent from a Glasgow accent or a Hebridean accent. Over time, both the way the language is spoken and the words used become characteristic of a region. When 2 ways of speaking a language have drifted sufficiently far apart, we call them different dialects. After enough centuries of drift, different regional dialects eventually become so different that people in one region can no longer understand people in another. At this point, we call them separate languages. That is what happened when German and Dutch drifted in separate directions from a now extinct ancestral language. It is what happened when French, Italian, Spanish, and Portuguese independently drifted away from Latin in separate parts of Europe. You can draw a family tree of languages with cousins like French, Portuguese, and Italian on neighboring branches, and ancestors like Latin further down the tree, just as Darwin did with species. Like languages, species change over time and over distance. Before we look at why this happens, we need to see how they do it. For species, the equivalent of words is DNA, the genetic information every living thing carries inside it that determines how it is made, as we saw in Chapter 2. When individuals reproduce sexually, they mix their DNA. And when members of one local population migrate into another local population and introduce their genes into it by mating with individuals of the population they've just joined, we call this gene flow. The equivalent of, say, Italian and French drifting apart is that the DNA of two separated populations of a species become less and less alike over time. Their DNA becomes less and less able to work together to make babies. Horses and donkeys can mate with each other, but horse DNA has drifted so far from donkey DNA that the two can no longer understand each other. Or rather, they can mix well enough, the two DNA dialects can understand each other well enough to make a living creature, a mule, but not well enough to make one that can reproduce itself. Mules, as we saw earlier, are sterile. An important difference between species and languages is that languages can pick up loan words from other languages. Long after it developed as a separate language from Romance, Germanic and Celtic sources, for example, English picked up shampoo from Hindi, iceberg from Norwegian, bungalow from Bengali, and anorak from Inuit. Animal species, by contrast, never, or almost never, exchange DNA ever again once they've drifted far enough apart to have stopped breeding together. Bacteria are another story. They do exchange genes, but there isn't enough space in this book to go into that. In the rest of this chapter, assume that we are talking about animals.
Islands and isolation, the power of separation. So the DNA of species, like the words of languages, drifts apart when separated. Why might this happen? What might start the separation? An obvious possibility is the sea. Populations on separate islands don't meet each other, not often anyway, so their two sets of genes have the opportunity to drift away from one another. This makes islands extremely important in the origins of new species. But we can think of an island as more than just a piece of land surrounded by water.